I'm going to hit the record button and yeah, let's just start. So welcome everyone to this again. So soon after the last one, another math reading group session. We're going to be talking about TDA or topological data analysis. Um, I will warn this is a pretty niche subject, and if you really want to like understand the math that's going on there, and it's worth at least understanding it, you have to go a bit far, but in practice, like it's a cool thing, but it's not like a magic bullet. So we'll see about that. So just let you know, but when I say this is a big subject, it's that okay that you have topological data analysis as a subfield, which is I guess a niche subfield of machine learning, but it's mostly like people who like topological data analysis that do topological data analysis, and it's not extremely used. And okay, a few people try to use it for machine learning or deep learning. Uh, I think it's niche. It's going to remain niche, and there's also sort of two aspects to it. So first, warning: the when we say topology here, we mean topology in the cup and donut sense that you can transform. Interesting instead of like general topology as we've talked before, it's more topological invariants and like deforming stuff under continuous transformations, somewhat related to the stuff we did on about Morse theory. So Morse theory is very much related to this kind of ideas, and you can see some of the ideas from Morse theory popping up here. Um, but that's for another day maybe. But there's sort of two aspects. So one is like studying topological features of data. So like treating your data set or data points as a something that might have inherently some kind of topology. Let's say that would come from something like the manifold hypothesis or whatever. And then there's stuff like data supported on topological domains. And that second part we won't be really talking about, but it's a pretty huge field, and it's like you can think of it as an extension of like geometric deep learning and sort of graph neural networks. You can easily like view that as a generalization of this idea. And I think this second part is actually the more interesting bit because it has more like relevant examples of models or situations where you might need to do this approach, where your data inherently lives on like these higher order domains. Like if you do geometry processing or mesh processing in Blender or whatever, you're doing this kind of stuff. You can do topological signal processing if you do like PDEs or trying to predict wind, then you might need that. Um, but that's for maybe another day. So just keep that in mind. Okay, everything still good so far? It seems so. So to give you like a brief outline, I'm going to start maybe in an unusual way in that I'm going to start with graphs and graph Laplacians. This might be surprising, but my goal with this is that like graphs and graph Laplacians are easy to understand, so that as represented by the small brain, and you can use that as an easy leverage to understand like simplicial complexes, and then later on this topology stuff, which is on its own very abstract and very difficult to understand. So my hope is that by starting with graph Laplacians and sort of like being gentle, you can get the harder ideas more easy. And then we'll finish with the more like application stuff in TDA, mainly via persistent homology. But I think we can look at one of the papers for that. They have like some nice visualizations. So let's keep going. So graphs and graph Laplacians. I should note also that I'm a network scientist by profession, and I really like spectral graph analysis. So also a bit of bias from me. So I think most of you should know what a graph is, right? If you have a set of vertices, usually a finite set, and a set of edges. So here an edge is going to be at, a pair of vertices. So this would be the set of pairs, not like directed, not tuples, but just a subset with two elements. And these would be edges. And so this represents, okay, points, my vertices, and then relation between these points. And so I have an example on the right here where I have, okay, 5 nodes and then no, 3 edges between them. And you can notice that, okay, there's one piece so 1, 2, 3 that's connected, and then 4 and 5 are connected, but there's no connection between the two. Um, okay, that's nice, but you can like transform it to another representation, namely matrix. So if you label the vertices here, I've already labeled them uh, 1 through 5, and so I can construct a matrix with a square matrix with size 5, and I put 1 in my matrix if there's an edge between I and j, and 0 otherwise. That gives me the adjacency matrix that like it completely describes my network or my graph. And okay, you might see here that because of the way if I get a lighter gray, you might see that because of the way I've labeled my vertices, it's like so a nice block structure that's apparent, right? I have the first 3 nodes that are in a connected component, they're sort of in a block, and then the other two in another block, and you can see that in between these two there's 0. So depending on what you've seen, when you see this sort of block structure in the matrix, you think, oh, that's interesting about the spectral properties of the matrix or whatever, and that's the idea. So uh, another matrix that you can construct based on the adjacency matrix is something called the graph Laplacian. Um, it's sort of related to like diffusion on the graph, but that's not important. If you take the sum of all the indices, all the m-terms on a row of the matrix A for row I, that gives you ki, which is the number of neighbors of node I, or also the degree. It's also called the degree of I. Now, if I put all these degrees in a diagonal matrix, and then take my Laplacian to be d minus a, I get another matrix called the combinatorial Laplacian, which it looks like, I mean, it's called Laplacian because it sort of looks like a discretized version of the Laplacian operator, which is differential operator, but that's not important. What is important is that this matrix L satisfies that it's easy to show, right? Because I've defined K as the sum of the Aij for each row, and then I've added the two. So now if I sum L along each row, I get 0. And same thing against each column. And that means that this sum I could interpret as just taking my matrix and multiplying that a vector with all entries 1, and that says me, okay, my matrix times this vector is equal to 0. And that's nice because that means that because this vector is not 0, this means that 1, this vector is always an eigenvector of my matrix L associated with the eigenvalue 0. And so I know now that 0 is always an eigenvalue of L, and actually it's more than that. The multiplicity, so the amount of times this eigenvalue appears in my spectrum is the number of connected components. So for example, if you look at this matrix here, I would have actually two. I could take just a vector of all ones for this block. That would be another eigenvector. All one for this block, it would be another eigenvector. So I have two, like a subspace of dimension 2 associated to eigenvalue 0. So the moral of the story here, and you should keep this in mind for later, is that I construct this matrix and look at the size, the like the dimension of the subspace associated to the eigenvalue 0, or also the kernel of my matrix, and that tells me about we can say a topological feature of my network, which is in this case the number of connected components. And we see that this will generalize for the kind of stuff we'll see just now. So, any questions so far? No? All right. So, as a sort of generalization of graphs, we can sort of think about simplicity. So, a simplex, let's say given a set of nodes here, I'm talking like very abstractly and sweeping some things under the rug. So, if I have some set of nodes, let's say 1 through n, a k simplex on my set V is going to be a subset alpha of here some, so it's going to be just a subset of these V. And if I need to visualize it, I can just like draw some pictures. So for example, if a k is equal 0, I only have one element in my set, and so that's just a point. if I have k is equal to 1, then I have two elements because I started 0 over to t, so weird conventions, but you'll see why. Um, then I have what we recognize an edge for from graphs. So this would be a one simplex, and then a two simplex. I have three nodes, and they form a triangle, and the triangle is filled, and so on. And so the reason we like say this is k equals 0, k equals 1, k equals 2, and so on, it's related to the sort of the dimension of these objects, right? A point is just a zero-dimensional object. An edge, you can think of it as like a one-dimensional object. A triangle is a two-dimensional object, and so on. And so this idea of like dimension here is the important bit, which is why we have this convention here. I should note a small vocabulary. When I have a simplex alpha, I'm going to say a face is just a proper subset alpha prime of alpha. So for example, in this triangle here, the edge along here is a face of it, and so is this vertex here. Okay, so now I have simplices, and I can sort of like glue them. Like in the same way a graph is like a combination of edges, a simplicial complex is just like a collection of simplices. And so a simplicial complex K, it's going to be a subset of all the power set of V, so all the subsets, but it has to satisfy some condition in that if for any simplex within K, K must also contain all the faces of this subset. So that's what I'm saying here for any simplex in K. If alpha prime is a face of alpha, then alpha prime is also in K. And so I'm gonna have like a small picture of this. So it's very weird, right? I have like a bunch of edges without face. I have one triangle here. I have a like a tetrahedron here. So you can mix and match stuff and make something weird. Um, to illustrate maybe this condition, so these three examples on the left, sorry, here are all simplicial complexes because they all any simplex also has its faces in the same complex. But this last one is not because okay, I only have the triangle, but I don't have the edges or the nodes. So that's the idea. Okay, so more definitions, but then we'll get to the fun stuff. So if I have a k simplex or a simplicial complex here, we're going to say the dimension of my simplicial complex is going to be the dimension of the largest simplex in it. So for example, in this case, it would be 2 because I have this, maybe, no, 2 or 3. I'm sorry, 3 for this one. Um, so this is the dimension. A small definition, but it's not really important. If I have a simplex, I can sort of like filter all the simplices above a certain dimension. It becomes something called the k-skeleton of it. And for example, if I take the one skeleton, that just gives me a graph. So it's nice because you can sort of always like filter stuff out or get simpler objects. Um, Another thing, a facet of my simplicial complex is going to be a maximal element of K. So just any simplex that is not a face of any other simplex in my simplicial complex. So for example, in this case, I have this as a face, this is a face, and then these three edges are faces. Facets, sorry, not faces. The important, why this is important is that if I know exactly what are the facets of my simplicial complex, I know exactly what my simplicial complex is. So if you were to try to like implement this in a computer, you would not need to have like a set for all the subsimplices, you just need a list of the facets. Now, okay, simplicial complexes are nice, but there's a whole zoo of variations of them. So one of them is called a pure simplicial complex. That is simply a simplicial complex where all the facets have the same dimensions. And so I have an example here. I can be a bit more restrictive and also ask that it's like a manifold. I don't give the exact definition of a discrete manifold here, but the idea is that it still needs to be pure, but I also need some conditions on how my facets are allowed to connect. So for example, like this connection here does not look like manifold because I have a pinch, and here I have like two flaps, so that's not manifold. So if you add these conditions, you get a discrete manifold, and it's really like a discretized differential manifold from differential geometry. And it's nice because like, you can really have like some form of like discrete differential calculus on these objects. So they're very nice to work with. Um, I mentioned meshes at the beginning. So sometimes you do not have like triangular face or whatever. You might want to have like rectangular faces or more. And so for that you have something called cell complexes, where you may have groups of face might be have any number of points, but you know okay this is a face. Volume can be have any number of vertices, but I'm saying okay this is a volume. And then if you want less structure, you can also do what's called a hypergraph, not to be confused with a hypernetwork. So a hypergraph is just a arbitrary collection of subsets of the power set of V with no additional conditions. So for example, this is just a hyperedge um, with three nodes, another with two, and so on. So there's these dual things, and they can be useful for different problems. So for example, a hypergraph might be really good if you try to model, say, a citation network, or you have a list of papers. Each paper has like a certain list of authors. You might say, okay, each paper is a hyperedge with for all the authors, and that fits well. Some other problems you have more structure, and you might want to use a simplicial complex. Um, I think Tonic, could you mute your mic, by the way? Thanks. Um, so just letting you know that depending on what you're trying to model, there's a whole zoo of things you could use. But we'll be sticking with simplicial complex for today. Okay, now comes the first fun bit. So Betty numbers. I'm going to give the intuitive version first, and by intuitive I mean like high level and mostly for like smooth stuff. And what we'll do next is like build that to get like a proper definition, but for a discrete case. So I'm going to say the Betty number, beta m, of a topological manifold, so think just a ball of dough, it's going to be the number of m-dimensional holes in it. So now you might ask, okay, what the hell is an m-dimensional hole? Um, that is the thing that we'll need to spend time to define exactly, but for now, bear with me. So I have a few examples here. So beta 0, I'm going to say is just the number of connected components in my manifold. So connected components, okay, we can sort of understand that. Beta 1 is going to be the number of one-dimensional cycles in it. And so, for example, okay, in all of these examples, like I have a circle, yeah, just a circle, so no inside. Okay, it has one connected component, it's just one piece. And then, okay, obviously it has one cycle, right? I can have a loop, I cannot really like cut it or shrink it down. So I have one connected component, one cycle, and then it doesn't enclose any volume or whatever. So it's beta 2 is going to be 0. Now if I take a disk, so it's the same as a circle, but now I filled in the inside. Okay, it's still one piece, so beta 0 is equal to 1. But now I have no more cycle. And why? The reason for that is that any like I can take the outer cycle, but I can shrink it down to a point. I can sort of whoop, and because I can shrink it down, that means that there's no actual like real cycle within that. Um, we'll see more example of this later. If I take a sphere now, a sphere, okay, it's a 2D surface. It's still uh, one connected component. Still no cycle for mostly the same reason as the disk. But then now my sphere, it's like it's cutting off. It's a bubble. Like there's an inside and an outside the sphere. And so I say that it's going to be one enclosed volume. So beta 2 is going to be equal to 1. Okay, so far so good. Um, this last example is a torus. So you can think of this as a donut, but without the inside. Okay, of course, just one connected component, one enclosed volume. Now, notice that here I'm saying there's two 2D cycles. Now, does anyone have any idea why that might be? Like, where are these cycles in this? No one wants to guess? Yes, I am talking about the torus and asking if anyone knows why the beta 1 for the torus is 2. Might be easier if I do a bigger drawing. So, oop,
I think I have the answer.
go on.
Um, it is the circle formed by the inner edge of the hole and the circle formed by walking around through the
Yes,
hole.
exactly. So I have one cycle here that I cannot shrink, and then have another cycle precisely around I think if I, around the equator. So I have two cycles and they're different. So indeed, so in this case, the torus has exactly this. So this is sort of give you idea. We will see like a nice, easier definition of this, but that's the intuition, at least for this kind of stuff. And actually, we see that in the discrete case, it's going to work the same, or at least mostly the same. So, okay, Belly numbers are fine. The important bit about Belly numbers is that they're topological invariants. That means that I can like deform my torus or deform my sphere. The Belly numbers are going to stay the same, and that's important because I can have data that's like one of these simple shapes, but like very fucked up or very distorted. If I recover the topology and compute the Belly numbers, I can immediately know what it looks like. Um, that doesn't mean that the Belly numbers completely describe a topological object, but they're still very interesting to to look at. Okay, so um, how do we like formalize this, at least in the discrete case? To do that, we'll need to first give some direction. So like all of these parts is going to be seem a bit mysterious at first, but then when we'll see the payoff. So bear with me. So we'll need first to like give a direction to my simplices. So to do that, okay, let's say I have a simplex V0 for Vm, so m plus one dimensional simplex. No, just m dimensional simplex. Sorry. I'm going to give it an orientation, which is just going to mean that instead of a set, I use a tuple V0 for Vm. But then there's sort of an additional rule, which is that if I permute my entries in this tuple, I change the sign, and with big quotes here, the sign of my orientation based on the sign of my permutation. So if I have a permutation pi that permutes these vertices, or yes, these vertices, um, this object here, applying the permutation, is just going to be changing the sign from this original object, and the sign is just the sign of a permutation. So I have an example here. If I have just an edge, an oriented edge, so uv, that's going to be the same as minus vu. Okay, so far so good. Um, an oriented triangle, okay, so so UVW is going to be minus UWV, and so on. And I have listed all the possible permutations. So notice that, okay, for edges, it's sort of this an intuitive like way to represent this like directionality, right? It's, okay, UV is just U going to V, VU is V going to U, and then triangles, they can also do that, maybe in a bit strange way, right? Say UVW is like an arrow going in this way, so like around, let's say in the uh, sorry, the clockwise, sorry. So UVW goes clockwise, and then UWV goes counterclockwise. Um, if you've done anything with like differential calculus, this might remind you something. Uh, Keep that nugget in mind. If that doesn't remind you of something, that then carry on. So okay, we have like nice ways of representing these, at least for one dimension, two dimensions. Above it, it's a bit trickier. But okay, we now we have direction, and so now I can form what's called an M chain of my simplicial complex. So we're going to call an M chain, and this is the weird part, a linear, formal linear combination of the oriented M simplices. So that's a mouthful. So it's just think of it as like an algebraic expression where I have my oriented simplices of the same size. So let's say just have 1, 2, minus 2, 3, plus 2, 4. That's just going to be this thing here. So I have 1, 2, so 1 direction directed to 2, minus 2, 3, so 3 going to 2, plus 2, 4, so 2 going to 4. Okay, that's an M chain. I can do that with triangles. So let's see, 1, 2, 3, minus 2, 3, 4, minus 3, 4, 5. So I have 1, 2, 3. That's a triangle going this way. Minus 2, 3, 4. So that's a triangle going this way. So yeah. And then minus 3, 4, 5. So that's a triangle going this way. Okay. Why are we doing this? The point is that now we have like an algebraic way of expressing simplicial objects. And the algebraic part here is nice because we'll be able to use tools from that. And so in fact, we have more than that, although I'm sweeping quite a lot of details under the rug. We have what's called a vector space of like M chains, or we can easily like modify to have a vector space. So if we have a vector space, we're happy because we can do linear algebra. And that's exactly what we're going to do. So we have this thing called a boundary operator. Recall that in topology, the boundary is like a map that takes, let's say, a set, field set, right? In topology, the boundary might be taking like a closed set and then just returning the outer shell. We can do that in like in the discrete sense too. And because we have vector space, we can actually do that as a linear map. So I claim that the DM for yeah DM, the m-dimensional, not sorry, the boundary operators on M chains is going to take an M chain and return an M minus one chain, and it's going to be linear because I have vector spaces. The definition is okay, a bit not nice, but if I have a M simplex and take the boundary of that, it's just going to be this big sum, which is just again a linear combination of all the sub faces m minus one faces of it. And notice okay, I have a sum over p all the way to m, and then okay, I have something that depends like minus one to the p, so I have a sign, and then I'm just taking the sorry the simplex and I remove v of p. It's easier to do with an example. So what happens if I take the boundary of an edge, let's say 1 versus, directed to 2? Okay, that's going to be, well, first I remove 1, so I get just 2. And then minus, I remove 2, and then I get just 1. And okay, so notice that the boundary of an edge is just the two endpoints directed. And this might seem a bit, if you remember your calculus, like if I take the integral from a to b of f prime of x, that's just f of b minus f of a. This is in fact not an accident. This is very much the same kind of thing that's going on here. The more general notion of this is called Green's theorem, and here we have like a discrete version of Green's theorem, so exciting stuff. But anyway, so let's say what happens if I take the boundary now of a triangle. Okay, so the 1, 2, 3 becomes, again, I remove 1, so I have 2, 3 minus 1, 3 plus 1, 2. Okay, if I draw this, I get this. I have, okay, an edge from 2, 3, an edge from 3 to 1, and then an edge from 1 to 2. Okay, nice. What happens if I take the boundary of this? Okay, I can compute. We now know how to compute the boundary of edges. So it turns out that I just get 0 because all of these terms cancel out. And so that's important takeaway one. The boundary of a boundary is always 0. So the boundary of something has no boundary. this is like a property term. So uh, formally, we can say, okay, the if I take the m plus one boundary and come do that after the mth boundary, that's always going to be equal to zero. So important bit. And so an m cycle, we can define like an m cycle as an m chain with no boundary. So essentially a chain such that this is satisfied. And if you want to know the intuition for cycle, well, look at this bit here, right? I took the boundary of a triangle and I got like a nice directed cycle. It's like a little loop. That's the idea of a boundary, or what we call it a cycle, and that's what we're going to use. And now, okay, if I look at the space of cycles, so by this equation is just the kernel of d of m. That's going to be a subspace of my vector space of m chains. Um, we can find like we can look at the kernel of this operator and say, okay, which of these cycles come from higher order, like which of these cycles are the boundaries of something else, and which of them are not. Like it's not guaranteed that all my cycles actually come from the boundary of higher order M chain. And so whenever I find one of these cycles that is not the boundary of an M plus one chain, well, I'm going to call that an M cycle. And so as an example on the bottom here, okay, I have this simplicial complex. We have that, so 2, 3, 3, 4, minus 4. So this like cycle here, this is a one cycle because the inside triangle is not filled in. So it is in fact a hole in my complex. Was 1, 2, 3. It's not a hole because it is the boundary of the triangle 1, 2, 3. So that's the big idea. And now we can start doing things. So I have two things. I have the image of the m plus 1. So those would be the boundaries. Obviously, it's in the kernel of the boundary of the m. And so if I want to separate these two. I would like to say, okay, the kernel without the image of the m plus 1 is going to be my space of holes, or you might say cavities. And there's more structure to this. We can say, okay, this is actually a group called the homology group, and it's going to be the quotient space of the kernel of the m by image of the m plus 1. If you don't know what quotient space means, don't worry too much about it. Just keep the idea that we sort of like only remove the boundaries and only keep the non-boundaries, only keep the holes. But take your time if this is confusing. And now I can say the Bally numbers, right? I mentioned this as the number of like cavities. I can actually define that as the rank, or really the dimension in this case, of HM. So it's going to be the dimension of the kernel minus the dimension of the image of, so the dimension of the kernel of the M minus the dimension of the image of the M plus 1. Okay, so far so good. Um, another notion, but more in the continuous case, but actually it also sort of applies in the discrete one. Okay, here I have not a torus, but like an annulus, so it's like a disk, but the center is cut out. Here I have, okay, two cycles, or yeah, two loops in orange and blue, and I'm going to say they're equivalent because I can sort of like continuously deform one into another. So these are equivalent, but then the purple one and the green one, they're equivalent with each other, but they're not equivalent to the other two. And so this is another idea, or the group. Like you can really like turn this in like a proper group, but probably not the time for it. But when I say quotient, it's by an equivalence relation, and this is the kind of equivalence we're talking about. So, but keep in mind that okay, we can do this in the continuous case, but we're really doing that in the discrete case, and it makes things tractable. And that's the nice important bit, because you can always discretize like a smooth manifold. You can like, discretize it by a simplicial complex and compute the homology, and it's going to work too. Okay, but you may ask, okay, how do I actually compute this homology? And now we sort of come back to the first bit about graph Laplacians. So the first bit we need is that because these are vector spaces, I can choose bases for them. Uh, to do that, I just like pick an order for my vertices and simplexes and like express my matrix. And so, okay, so this matrix here is just the representation of the boundary operator. So like, oop. So the boundary operator, it's a linear map. I can express it in the basis that I've chosen. The actual basis is not important. Um, but I'm going to say, okay, the entry between index alpha prime and alpha is could be minus 1 to the p if alpha is so v0 to vm, and then alpha prime is just one of these facets with v of p removed. So again, probably better to do an example. Let's say I have this simplicial complex, so I have a triangle and then an edge sticking out. Um, the matrix representing the D1, so this is D1, it looks like this. So it goes from edges to uh, vertices, and it looks like this because I have, okay, taken my edge 1, 2, 2, and then, okay, because by definition of the boundary operator, okay, I have 1 for minus 1 for 1 and 2 for 2, and then 1 for 2, and then 0 for the other 2. And then I can do that for every single edge. Okay, I can also look at the representation of D2 because I only have one triangle. There's only one entry, and then I just have 1 minus 1 0. Okay, so far so good. So I can like boil it down to linear operators and then to matrices if I choose a basis, and then I can sort of construct an equivalent, like a higher order equivalent of my graph Laplacian that's also going to tell me about like my Betti numbers. So if I define the Hodge Laplacian as the following, so I'm taking like Bm transpose Bm plus Bm plus 1 transpose Bm plus 1 times Bm plus 1 transpose. Notice that because this operator it goes from m chains to m minus 1 chains, the transpose goes through from n minus 1 chains to m chains. So I go m chain. I take an m chain, I go back to go down to a m minus 1 chain, and then I go up again. Here I take an m chain, I go to a m plus 1 chain, and then go back down to an m chain again. So it's sort of communication at like the two levels above and below. Notice that this is going to be a symmetric matrix, and okay, I can construct it for this example. So a similar example as previously. Um, I've constructed like the L0. Notice that for L0 there's no like lower level, and so I'm just going to say 0. Um, so if L0 is just B1 times B1 transpose, if you look at it, this is actually just the graph Laplacian we had in the beginning. At least you can convince yourself it is because like these minus ones are just the entries of the adjacency matrix, and these two are just the degrees. So it is in fact the graph Laplacian. And remember, I mentioned the dimension of the kernel of the graph Laplacian is going to be equal to the number of connected components, so beta 0. It's going to be the same for L1. So if I take L1, which is again this big matrix, notice that if you look at B1 transpose and B1, this is also an interesting matrix in and of itself because it's sort of the Laplacian matrix of the line graph, which is sort of a graph where you flip vertices and edges, but not too important, but to give some intuition. And so, okay, I have a new matrix. I can look at the kernel of that matrix or operator, and actually the dimension of the kernel is going to be the Betti number. So in general, the Betti number Betti m is going to be the dimension of the kernel of the mth order Hodge Laplacian. So now it's nice. We've boiled it down to like a completely standard, easy to compute thing instead of the intuition. So hopefully that was insightful, I hope. Okay, so now we're going to sort of go back to more practical things. So Okay, now we know about how to do this homology and so on. How do you use that for data? And so the problem, at least in topological data analysis, is given some finite data set, we can assume in RD, can we like recover its inherent quote unquote topological features? And as mentioned, this is related to the idea of the manifold hypothesis where your data is supposed to be on a manifold. Problem, okay, if I just have a point cloud, a point cloud is just a bunch of zero-dimensional objects, so it's not interesting. The idea of TDA is to construct simplicial complexes from the dataset. In fact, not just one, but like a sequence of simplicial complex, and then looking at this sequence and like the homological properties, like the Betty numbers of at each time in a sequence, that's going to be usually telling me about what's the topology of my dataset looks like. So the most common like way to construct a simplicial complex from a data point used in TDA because it's the practical one. So if I have metric space, so in RD I can just use a Euclidean metric or whatever, but it works for arbitrary metric space, and I pick some r greater than 0, then the Vietoris Rips complex, there's many ways to construct one, but the Vietoris Rips is one of them. It's going to be the simplicial complex VP of R, VPR of V, such that so a simplex is going to be in a VP if and only if for any P and Q in alpha, the distance between P and Q is smaller than 2R. Okay, that's the written definition. The intuitive idea is that I look at each point, I draw a small ball of radius epsilon around that ball. If it intersects with any other ball, I'm going to connect these like, okay, here I have nothing, but if I take larger balls, you can see that now a couple of these balls intersect, and so now there's an edge between these points. So sorry, it's tiny, but that's the idea. If I now have like a group of 3 points that all have their balls intersecting, then I'm going to draw a triangle. So straightforward, but a bit expensive, right? Because you need to compute the distance between every pair of points. So a bit unfortunate, but we can deal with that. And that gives you a simplicial complex. Now, obviously, a priori, you have no way to know what's the right R to choose. And so typically, you're going to look at the sequence of the simplicial complex as you increase R from 0 to infinity. But in practice, so okay, let's say for sufficiently small R, I only have like zero-dimensional simplices. Then I get like maybe some edges, and then something more complicated. And then if I take R large enough, I just have a single simplex that has all the vertices in it. So at some point I can stop. So I have like a sequence of simplicial complex. They're also all included one in the other. So this complex is included in this one is included in this one, and so on. So I have like a monotonic sequence of simplicial complexes, also known as a filtration, and I can look at. So sorry. So more yeah, going to stick with filtration. So formally a filtration is just a sequence of subcomplexes that so you can think of it as growing in time. They have to be included in one or the other. So we just saw the Vietoris Rips complex. There's another one, like say you have a function defined on the node. You can define your filtration just by taking the level sets of this function on your node. That's one way, and it's related to the Morse theory we saw a while back. There's some other stuff called the check filtration and so on. Really, the Vietoris rips and maybe the space filtration are the most useful here. Now, okay, let's assume you have like this sequence of simplified complexes. Um, you can look at the homology, so the compute the Betty numbers at each step of your sequence, and then track the evolution of topological features. So especially when do I get like new cavities or cycles, and when do they start appearing, when do they stop? So if I look back at this, right, you can imagine that at some point when I have R large enough, I'm going to have like a loop of vertices. And then at some point, the loop is going to be absorbed into a higher order simplex. So that's what we call by birth and def. And so, okay, we record the birth and def times of all these cavities, and that gives me like a data set B of BI and DI. Okay. Um, there's also two like very common ways of looking at them. One is called the persistent diagram, where you plot all your birth and death as points on the plane, and then you compare against the like y equals x line. And the idea is that okay, points far near the line, they're going to be points that die very soon after they appear. So that's probably not something like that's very relevant. It's probably maybe more noise. On the other hand, if I have like a point that's far away from the diagonal, that means it's a cycle or a cavity that stays for a long time. So that's maybe more like a proper feature, topological feature of my dataset. There's another way of looking at these called a barcode diagram, where you just like stack. So each line is just a cavity, and it's like it goes from the birth to the death. And so again, it's another way of looking at it. So I have no more slides, but I do have. Oop. Uh, yeah, there you go. This paper, which is very short and actually gives like a very nice overview. Unfortunately, my mouse is very trash, but they give you like a nice overview of what we just talked about, and especially other examples. So if we have another example here, maybe a bit more telling of a filtration, right? I start as epsilon 0, okay, no things, and then if you look at these data sets, they sort of look like a cycle or like a circle, and I can sort of recover that if I take a large enough filtration, right? At some point, I just one cycle. It's now I have a cycle, then it goes all gets absorbed, and I'm not exactly entirely clear how they constructed these because it's confusing to me, but anyway, this is what you typically would do. Um, One thing to note, okay, these are like visualizations. One problem you might have is that if you want to do like machine learning, you can sort of use that to extract features, but there's no super obvious way. They mention a couple of them in the paper, but that's one difficulty you have in integrating TDA workflows in like machine learning is that you need a way to go from these features, from these like uh, persistent homology features, back to vectors or something you can feed into a neural network. That's not super easy. Boop, boop, boop. Let's see. Yeah, here they show examples of like stuff with the level set of a function I mentioned. And I think they mentioned yeah, here, for example, they use sort of amplitude and entropy of these persistent diagrams as a way to get like just vector data out of it. And then they show okay correlation. So for example, here they use it on MNIST. They use a few different filtrations on MNIST. And here each image is considered as a point cloud or whatever. So they use a few of these, compute these amplitude and entropy features, and then they sort of find that okay, you can reduce it to like only 28 topological features to solve MNIST. Note that I think they mentioned at the end, okay, we can only need 28 features, but it only reaches like 96%, which not that great on MNIST, but that's the gist of it. So that's sort of what I had to talk about. I will say, so TDA is nice, maybe not like super straightforward to use in every single case, but nice enough to know. The one like big problem with it's that it doesn't scale super well because you need to be computing like this persistent homology, which means you need to look at every pair of points. So for like the large data set, large point clouds, that gets really expensive. And so I think that's like probably one of the main reasons it's not like more adopted is that because it's so expensive at scale. But anyway, with that, if anyone has questions, please ask them. Okay, so no apparent questions. Maybe one. The Python TDA, like if you do want to play with this, there's a nice package which I did know about before someone mentioned it in general. Python Jota TDA. There we go. Sorry for the non-black, but yeah, if you would like to play with this, there's a nice Python package for it called Joto, which does a bunch of these things, and I think it can integrate into SciPy. I swear I saw something for TDA in JAX, but I couldn't find it, so maybe I hallucinated it. But yeah, if you want to play with it, there's a bunch of there's a nice Python package for it. Okay, still no questions, not even in the thread, not even the thread. Maybe one question. Okay, enjoyed the talk too. Okay, thanks. So I'm guessing no one, this was perfectly clear and no one has questions, which yeah, probably I should hope that's the case, but I'm never sure. But anyway, um, so if really no one has questions, then I think we can end. That leaves sort of the choice of what to cover next. Um, Keeping in mind that I might like take some time off, and because it's summer, I assume other people will be taking time off. So, okay, how to scale up would be my question. Ooh, that I don't know. I think it's about like probably algorithmic progress, but maybe just having like very beefy implementations. Like let's say someone makes a Rust package for TDA and like does computes the homology super efficiently, maybe. But then the other problem would be how do you integrate that with machine learning when you need to do that on GPU? And I don't think persistent homology is a very GPU friendly um, computation. It might be, but I've never seen anything about that. So probably if you like go full bitter pill about this, yeah. But that being said, there are cases where it's useful to use TDA. It's just there's not that many cases. Okay. So that there was one question. So yeah, back to the what I was saying. So I'll announce, but probably for the next time, either something about the RWKV, which I think I would like to cover if I find like good enough sources. Otherwise, if I remember the poll, let's see, what did the poll say when I made it last time? Okay, so topological data analysis was the winner. Second one is functional data analysis. That would be nice to do too. Um, yeah, so functional data analysis and then or after RWKV, then yeah, we'll see what we do. Yes, FDA is very nice, although it suffers from the same fate as TDA in that it's maybe not super applicable in many instances, but it is worth looking into. So I will enjoy doing it. Anyway, so I think we can leave it at that. So thank you everyone for attending and for listening to this and hopefully getting some nice math out of it. And so I think we can say goodbye.